motion is a kind of oscillation. An oscillation is a repeated cycle of motion, and it has a fixed time interval t, which means it's periodic, and the reciprocal of t is f, and the angular frequency, which is the angular f, is 2 pi f. And when we talk about angular frequency, we're going to measure it in radians, and radians can be shown as 1 radian, which is that angle where theta is the angle subtended by the arc of length r at the centre of the circle. Simple harmonic motion, or SHM, is defined as when the motion of a particle is proportional to its acceleration, and the acceleration of a particle is in the opposite direction to its displacement and is proportional to it. So we can write this as an equation, which is A is proportional to minus x. So we can see this when we have our pendulum, because when it's in the centre, it's got no displacement and no acceleration, and then up here it's got high acceleration and high displacement, but they're in the opposite direction to each other. Whee! Okay, examples of this include an iceberg popping up and down in water, a pendulum, we have some more here, water in a U-tube, mass spring systems, so they're like those boingy things, and a ball on a parabolic track. Simple harmonic motion is sinusoidal with respect to time. So if there's t on the x-axis here, then up here, let's say we've got displacement here. And now if it's starting here, this particle is going to go like that. And this is its displacement. It's always hitting max displacement here, and displacement here. And then this can be written as an equation as x equals, so you've got sine t because it's sinusoidal, and then x0 here because this is x max, and that's the maximum value of it. Now let's say we had something that started up here and then went down like that and along and so on, so we're starting at maximum displacement instead of minimum, then that just means that we are going to have to use cos t instead of sine t, or just change the extra phase difference here, but deal with it when it comes. If you need velocity, then you can find the gradient of this, so that's going to be 0 there, maximum there, so it's kind of switched a bit. And then acceleration, do the same but to the velocity graph, so the derivative of the derivative of this, so double derivative. Now, imagine if we have a displacement graph again, as we had earlier, but this time up here we're going to have the energy of the particle. Now the particle is always going to have the same total energy, ET, but the distribution of the energy is going to change. So when it's at the centre, it's going to have its minimum potential energy, so that will be here, because it's still a little bit above the floor if it's like this. And then it's going to come up like this, and that there is EP, and then kinetic energy is the opposite, because they add up to make the total energy. And there you have the energy. In a standing wave, there is no net energy transfer, and all the points in a node-to-node loop are in phase. Node is one of these places where nothing is moving. See, there's one here, and one here, and then here we have the antinodes, which are the places where the particles have maximum amplitude. So that's their maximum displacement is the maximum. And here is the equilibrium position. Standing waves can occur in strings and in pipes. If they're in a string, or if they're a pipe with two closed ends, then we get this kind of shape like a beam. And they're going to go up like this, so you get one, and then you get another one, and they've always got this dot and dot, so they've got a node at both the ends. And we can calculate their wavelength by doing 2 times the length of the pipe, so that's all the string, divided by the harmonic. Now, if we go up one, so we've got half and half, so this is in a pipe. If you've got one end closed and one end open, here's the closed end here, and there's the open end. And so you're going to get this kind of thing like a fish's nose. And then the next one, you're going to get an actual fish. And then the next one, you're going to get a really weird fish. So then we go up one more. Oh, this one, the lambda equals 2L. No, sorry, lambda equals 4L over the harmonic. Then up to the next one, we've got a pipe with two open ends. So if the pipe has two open ends, then there are two of these wide things here. So you're going to get a kind of cross, and then you're going to get a crisscross, and then you're going to get a really crisscross. Yeah, crisscross. And this one, we're going back to the beginning one, so we're going to get lambda equals 2L over the harmonic. And the numbers of harmonic go up normally for the first one and the last one. So if you've got both the same, then it's okay, we're going to go 1, 2, 3, and so on. But if you're in the middle one with half and half, so your little fishes, then you're going to get 1, 3, 5, and it's the odd one out, and it also has odd numbers. So that's nice, and it also has odd little fish. Travelling waves can be described by the formula V equals F lambda, or fighting giraffes, where V is the velocity of the wave, and this is determined by the medium the wave is travelling through, and it's the distance travelled per unit time by the energy of the wave. And F is the frequency of the wave, and this is determined by the source of the wave. And here we have lambda, and lambda can be shown on a graph, and it must be against distance here, and over here we have x as displacement, which is the distance in a particular direction from the mean position. And so here we have our wave, and the wavelength is the distance between successive crests or successive troughs, and it's the distance travelled by the wave in one oscillation of the source. So there we have the wavelength, and here we have the amplitude, which is the amplitude A, which is the maximum displacement from the equilibrium position. And we can also have this other graph, which is very similar, or at least it looks very similar, but along the bottom we've got t time, and then we're going to have that again, and displacement over here. And again we've got amplitude here, but instead of wavelength along here, we're going to have t, the time period, along the slit interference is where we've got one slit, and then we've got a screen over here, and say this is a line normal to both the screen and the slit, and the screen's of width b. So then any point in here is going to be an angle theta from the normal. So if we draw that out like that, and there's theta. And the points on here where there's going to be a maximum intensity of light, so if you've got light shining through that and it's all coherent, which means that there's a constant phase difference between any two rays of light, then over here we're going to be getting this kind of pattern. And that's where theta, because at small distances then theta is about sine theta, and sine theta we can show is lambda over b. And so at the points where the path difference is lambda, then they're going to be in phase, which means that we're going to get constructive interference. And where the path difference is half lambda, then there's going to be destructive interference because it's a half of the wavelength. As the width of the slit decreases, so as B decreases, then the light becomes less intense, so it's going to be fainter because there's less light coming through. But the width of the central maximum is going to increase. So it's a smaller slit, but it's a bigger central maximum. And as the wavelength of the colour increases, then diffraction increases too. And if you